Hello, everyone. Thanks for joining us. I'm Chris Tillman, Director of Business Development at Interface Fluidics. Our presenter today is Stuart Kinnear. He's the CEO and co-founder of Interface Fluidics. Today, he's going to be talking to you guys a little bit about our new and exciting product, MMP. So feel free to ask any questions on the chat function. Oh, there we go. On YouTube, or at our email address, webinar@interfacefluidics.com. Be sure to visit our website. Hello, everyone. Thanks for joining us. I'm Chris Tillman, Director of Business Development. Sorry about that. Got a little feedback. Be sure to visit us at our website at interfacefluidics.com if you already haven't. I'm going to hand it over to Stuart here, and he'll lead you into the MMP discussion.
Thanks, everybody. As Chris mentioned, I'm the CEO and one of the co-founders of Interface, and I'm really excited to talk to you today about what it is that we're doing at Interface, why it's exciting, the direction we're going as a company, and sort of the short term, how you can get involved. So we're here today to talk about microfluidic minimum miscibility pressure measurements. And as a lead-in, this is a product that was developed in partnership with Equinor in Norway, as a result of Interface's partnership. And what we set out to do was to develop a replacement for traditional slim tube measurements. But I'm getting ahead of myself a bit here. And the reason that we did this is because that together we identified that we believe that minimum miscibility pressure measurements, or slim tube, is a measurement that's been held back by traditional measurements and methodologies. And so we asked ourselves some fundamental questions. How can we think differently about minimum miscibility pressure? Some of the questions that we heard often were, what would we do if a slim tube experiment took 4 days and cost 80% less than it currently does? And how many compromises are we making on a day-to-day basis because samples are just too scarce to get? And the final one is, as the carbon economy starts to mature, could this accessible minimum miscibility pressure data open up new options for enhanced oil recovery, improved oil recovery, or carbon sequestration? So these are the kinds of questions that we had in our mind when we were developing this technology, and that's why we're doing it. So today, I'll run you through an introduction to Interface Fluidics, talk to you a bit about our long-term vision and what we're building at Interface. I'll run through the specifics of our method for minimum miscibility pressure measurements, and then we'll have a Q&A portion where we're happy to have a conversation about what it is that we've presented today. As Chris mentioned, please drop your questions in chat as we go along here. So Interface Fluidics is a company that was founded in 2016 by myself and my two business partners, Tom DeHaas and David Sinton. We have our facility at the National Institute for Nanotechnology in Edmonton, Alberta. The National Institute for Nanotechnology is Canada's national research center for all things nanotechnology. And that's why we're there alongside some of the most cutting-edge companies in all of Canada. And from this laboratory, we provide unique insights into the interactions and properties of reservoir fluids in order to improve the operating efficiencies and enable better long-term decisions for our customers. Our goal is to make extreme condition fluid analysis ubiquitous and accessible, transforming things that were once considered difficult and expensive to get. We want to bring those to the masses and bring real-time fluid analysis to the world. We provide solutions in a number of different parts of the oil and gas industry, primarily into 4 big buckets. The first is phase behavior studies, which obviously is part of what we're here to talk about today. But we've also been providing enhanced oil recovery, hydraulic fracturing chemistry analysis, and SAGD thermal enhanced oil recovery opportunities and optimization for the last 5 years. Our technology has been featured twice in the Journal of Petroleum Technology, once for our hydraulic fracturing technology, and just this week for our minimum miscibility pressure measurements that we're all here today to talk about. I wanted to give a quick call out to our partners at Equinor, who actually are providing the cover art and the cover article that was featured in this month's JPT. You can see we're not on the cover of this one, but we're featured in the article. So congrats to the team at Equinor. Our technology platform is built on a technology called Microfluidics, which is a technology that was adapted from the biomedical space, where it has fundamentally transformed the way that industries operate in the biomedical space. The vaccines that we're now all watching get rolled out around the world were developed using this technology. But at Interface, we took this and made it robust for the extreme conditions that the oil field demands. And what this allows our technology to do is deliver better results than traditional lab tests much, much faster. And the second primary benefit is that for the first time ever, we're providing visual access to the porous media or to the experiments that are happening at a very, very high resolution. So we're actually seeing what's happening inside our reservoirs for the first time. Since we started the company, we've worked in many reservoirs around the world. So we've worked in everything from thermal enhanced oil recovery bitumen reservoirs in Alberta, all the way to tight, light shale down in the US, conventional reservoirs around the world, as well as select reservoirs in the Middle East, Norwegian continental shelf, and most recently on the east coast of Canada, offshore. This has given us a wide variety of reservoirs to work with, wide varieties of densities and viscosities, to the point where it's not really a thing that we have to worry about anymore. We've got a wide range of experience. As I mentioned, we've worked with a wide variety of customers, everybody from the chemical solution providers out there that are looking to validate that their products do what they say they're going to do, through the service providers, as well as the energy producers. So we've worked with oil and gas companies, chemical companies, and everybody in between for the last 5 years. So the next section of this presentation, I want to talk about Interface's vision for the future, because it's not limited to minimum miscibility pressure or enhanced oil recovery. It's a holistic vision of how we're going to transform the oil field PVT lab. So on this slide, I want to talk briefly about what our vision is for how the PVT lab of the future is actually going to work. You can see we've got one of our microfluidic devices there, and that's a Canadian quarter. On that device is 1,000 PVT cells. So if you think about the traditional PVT cell that's taking up half of a room, we've put 1,000 of them onto something about 1 millimeter by 1.5 millimeters. So it's something that's fundamentally changing the size that we're thinking about when it comes to oil field analysis. So our vision for the future is that our microfluidic technology is going to make PVT data accessible to anyone who needs it by reducing the time, cost, and sample size requirements associated with those measurements. And what that's going to do is we're going to move the industry to a data on demand model, as well as ongoing sample measurements, rather than take the sample and the measurement and rely on that for the next decade as we mature our reservoirs. We've already reduced the sample size requirements by 2 orders of magnitude, which is important because it allows us to eliminate the conversation of which data can I afford to collect with this 1 liter of oil field sample that I've actually got. No longer will it be a conversation about which data are we going to collect. We're just going to collect everything so we make the best possible decision. We're working to directly integrate into the simulation software that's already being used. And lastly, we will be establishing local laboratories for even shorter turnaround times. We're going to where the samples are stored. Now, it's been 6 years since we started the company, and a lot of folks ask us, well, what's your track record in this space? And the truth is that we've been working on phase behavior analysis for the entire time that our company's been existing. Even if it hasn't been the primary product that we've been able to commercialize. It takes a long time to build the infrastructure required to deliver the highest quality data that can compete with the highest quality service providers out there. In 2016, we had some of the highest pressure microfluidics capabilities anywhere in the world outside of academia. In 2017, we partnered with Total to develop the world's fastest and smallest diffusion coefficient measurement for heavy oil and solvent viscosities. We also increased our pressures to 100 bar operations. This is still low pressure in the world of oil and gas. In 2018, we developed our first wax appearance temperature measurements and validated those. We also made our first bubble point measurements. In 2019, things really started to accelerate. This is when we partnered with Equinor to accelerate our development, where we developed our first asphaltene deposition, we developed in situ rheology measurements, as well as published our first version of our phase diagram for gas measurements. We were able to make that 1,000 phase measurements, GOR, bubble point, dew point, critical point, all in one measurement. But that's just a prototype. In 2020, we finally finished developing our minimum miscibility pressure and greatly increased our pressure operations. And in 2021 and 2022, we're moving on to build the rest of the phase diagram so that you can come to us and be a one-stop shop. Black oil, condensate, live oil viscosity, density, swelling factors, and many other things. As you can see, one of the most difficult parts of microfluidics is increasing your pressure. And over the last 2 years, we've invested significantly in this to the point now where we're able to reliably operate at very high and reservoir relevant pressures, which was not possible until recently. And the question is, the technology portfolio that Interface is building is a full suite of PVT analysis. And so we're here today to talk about minimum miscibility pressure, but this is a small niche piece of what is the greater picture. And so beyond looking for people to work with on MMP, we're also looking for development partners that share this vision of the future with us, where we can miniaturize and standardize the phase behavior measurements of the future. But what are we here today to talk about? We're here today to talk about slim tube on a microfluidic device. On the right side of the page here, you can see this is the header from the Journal Petroleum Technology article that was published just a few days ago. And the idea here is that our technology is built, our minimum miscibility pressure method is built on our in-house microfluidic technology, as I've been talking about. And the goals that we set for ourselves when we started the development here was we need to be able to measure multi-contact miscibility pressure in 15 minutes using less than a milliliter of oil samples. And our goal was to deliver more data points that actually produced error bars on our data, reducing the error associated with traditional measurements, as well as getting visual access to these solvent-oil interactions that are happening to gain additional insights into what's going on inside of the porous media. And this is what we were successful at doing. So the next phase of this presentation, I'll just walk you through the details of our method, because as anyone in this space knows, if you're going to develop a new method, you have to make sure that you understand that you know you're making the measurement you think you're making. Otherwise, it's not a valid method. So our working principle, as in most cases, is very simple. We take the traditional slim tube, which you can see on the right side, and we've actually just replaced the slim tube apparatus with our microfluidic devices. And what that gets us is a miniaturized version of that slim tube. So we've got all the same control, pressure, temperature, flow rates that are associated with traditional slim tube, but we're just doing it on a standardized 100% repeatable platform that eliminates those errors and significantly reduces the time to make the measurement. Now, one of the things that I wanted to make sure we covered here is talking about imaging at Interface, because imaging is such a core principle to microfluidics and a core benefit to this technology and this specific measurement. And we use 3 different kinds of optics at Interface. We use fluorescence, where the oils that we're investigating are inherently fluorescent. So whenever you see an image with a black background and white images, that's the oil in the system fluorescing under UV light. But then if we combine that with bright field measurements, we can see the dark elements of the oil and gas, which means that we're able to actually differentiate solid phases from liquid phases. In this case, asphaltenes from the rest of the oil. And then by combining that with a third sort of standard measurement method, which is cross-polar microscopy, we're able to actually see crystalline structures like waxes, hydrates, ice, other crystalline formations within the system. So by combining fluorescence microscopy, bright field microscopy, and cross-polar microscopy, we're able to get the highest resolution phase differentiated images that are really possible in this space, making us able to make a really wide range of very accurate measurements. And this is what we rely on at Interface as our primary data collection method, with pressures and temperatures and flow rates all being secondary but also measured. So the question about miscibility is, how do we know we're at a miscible condition? So at Interface, we detect miscibility by measuring the local oil displacement efficiency. And what that means is we're looking at a subsection of the porous media near the exit of the porous media to investigate how much oil is in place after the CO2 front or gas front has passed. Because we're using porous media that's designed to replicate the porous media you'd find in a slim tube to encourage mixing and make sure that we have that multiple equilibrium contacts that is required in order to make a high quality measurement. When we're at or above the minimum miscibility pressure, the solvent oil interface disappears and local displacement efficiency approaches 100%. So what the beauty of this system is, it looks like something straight out of a textbook. And that's exactly what we're trying to do. So on this slide, I'll show you two examples of our microfluidic MMP method. This is a live oil sample. I can't disclose the location or the gas that's being injected, but it is at a reservoir relevant temperature and pressure. So on the left side, you'll see when I play the video what the immiscible case looks like. So I'll let this play here, but we can see, very standard viscous fingering effects where the gas is bypassing the oil. Lots of oil is left in place, and we have sharp interfaces between the gas and the oil. So if we look back at what the experiment looks like, there's lots of oil left in place. If I move on to the case where we've reached miscibility, what I'll do is I'll pause it right at the beginning here, because if we look at this first section, it looks very similar to what you would see in the first case where it's not miscible yet. And that's because we have to develop the miscible condition through the multiple equilibrium contacts. If I start playing the video again, you can see as we progress through the measurement that we have less and less oil left in the porous media. And we actually see the very hallmark of a miscible injection, which is a miscible zone, transition zone, where we go from immiscible at the front and miscible at the back. And we lose all of the interfaces between the oil and the gas. So this is a hallmark example of what miscibility in Interface's system looks like. And so the end of our measurement actually happens when we reach approximately 1 pore volume of gas injected. Basically, when we see the injected gas break through into the end of the porous media, that's the end of our experiment. And so we're measuring the oil left in place after that gas front has passed. And you can see the end state of this experiment versus the immiscible case is very, very different. And just to compare and contrast what that actually looks like, the reason we look at a small subset of the porous media is because in a traditional slim tube, we look at the effluent produced from the system in order to determine miscible condition. And the truth is that in those slim tubes, we don't have 100% miscibility from the first second. So that's why we don't get 100% displacement efficiency. At Interface, what we're able to do is just by looking at near the exit, we're only making the measurement where miscibility has actually occurred. And so we can see that we do reach that 100% displacement efficiency that you would expect. And you can see if we compare that subsection of the video in this frame, you can see the difference between what an immiscible case and a miscible case looks like at the pore scale. And the beauty of this measurement is that it takes 15 minutes to run this experiment. And so what we can do is, instead of running 4 or 5 miscibility pressure measurements and then interpolating the results, we make 10, 20, 30, 40, 50, if necessary, measurements to get a very, very high resolution measurement. And so in this case, we made 40 measurements in just 4 days, meaning that we actually get to the point where we have orders of magnitude more data collected, meaning we have high orders of magnitude higher resolution on this data and more accuracy. So you can see there's a sharp transition point here if we're looking at the relationship between percentage oil displacement and pressure as it increases. There's a sharp change in the characteristics of the oil that's being left in place. And that's the kind of investigation that our image processing algorithms are doing in order to determine that miscibility condition. These measurements were all taken using less than 5 milliliters of oil sample to collect all this data. And again, just to reiterate, in this case, there's no interpolation of the MMP being required. We're making the measurements repeat to make sure we get repeatable results at each pressure step. And then we use that in order to determine the miscibility condition. And so the last piece here is just to talk a bit about our operating parameters and the kinds of timelines that are possible with Interface. So today, our current operating pressures is approximately 150 Celsius or 300 Fahrenheit. And our pressure capabilities are approximately 640 bars of operating pressures. These are always a conversation. Unfortunately, today, before we move into a new facility, hopefully later this year, we don't have the ability to handle H2S, but that's on our development roadmap. When it comes to delivery timelines, samples where the minimum miscibility pressure is below 350 bar, it's approximately 1 week. 350 to 450 bar, it's approximately 1 to 2 weeks, though that's always changing and always improving. And then samples above 500 bars of pressure is approximately 3 weeks. But again, that's a moving target, and we're always getting better there. So with that, I'll say thanks very much and turn it over to any questions that have come in or any interesting thoughts that folks have. So thanks very much.
Awesome. Thanks, Stuart. That was quite intriguing. One thing I forgot to mention to you guys, this is actually our first webinar at Interface. So we're learning as we go, but I think we're going to have a schedule put up of following webinars on many different topics going forward. Like Stuart said, please submit any questions or comments you guys have onto the YouTube chat or at our website or our email, which is webinar@interfacefluidics.com. I'll start off with a question here. For the MMP, Stuart, what is the customer requirements?
Yeah, so we're able to obtain any of the sort of complex gas mixtures that are often required. We outsource those, so our customer's not required to provide those samples. All we need from a customer is a live oil sample. We need approximately 100 to 200 milliliters, depending on the conditions that are being tested, and that's sort of a target, not an absolute requirement. But beyond that, all we need to know is sort of the estimated MMP, so we can get started. It's a very, very quick turnaround, and we don't need much from our customers.
Right on. A question just came in on our YouTube chat. You mentioned the service. Do you sell the system including the visual cell and pressure containment?
So thanks for the question. No, we don't currently. We provide services exclusively at this point, and that's primarily because there's a lot of development happening behind the scenes, and as you can imagine, selling a pre-commercial piece of hardware is not a particularly good customer service experience. So we don't have the ability to support hardware in the field. I think one day in the future, that's something that we're always investigating, and future business models are always interesting. But for now, no, we're exclusively a service offering.
Okay, another question just came in. How do you determine the oil recovery for one slib tube run?
So I think that's again, we don't do slim tubes inside of our shop here, but basically the volumetric and gravimetric methods for determining how much oil is produced is typically used. In our system, we don't use any effluent measurements because I can give you an idea. The volume of our system is approximately 1 microliter to 10 microliters, depending on the measurement. And so there's just not enough sample in order to make a volumetric or gravimetric measurement. And so what we're doing is looking at visual, from the visual side, we're able to determine sort of nanoliter level accuracy in terms of volumes.
Okay, another question here. So when will the PVT suite be available commercially? That's something you touched a little bit earlier in the presentation there.
Yeah, so like I mentioned, it is a process that's under development, and as any development always goes, there's a sort of a range of timing that we're targeting. So we would like very much to have it ready and in the market in the next 9 months. But we believe that, depending on how development goes, it could take as long as 18 months. So I would say 9 to 18 months, and we've got a number of teams on these developments. And so these developments are all going to come to market at various times. And the full suite, we're hoping 9 to 18 months, but should be shorter for that with other measurements.
Awesome. Thanks, Stuart. Another question just came in on our YouTube chat. These new measurements, are these new measurements consistent with conventional slim tube?
Yeah, so absolutely. We've done a lot of work with our partners at Equinor. The development process basically was a blind test where they knew they had run slim tube experiments on all of the measurements that we made. And so we were able to recreate those measurements within our average error, or I shouldn't say average error, our average difference from the slim tube measurements was 2.3%. In most cases, it was less than 1%. And so it agrees very, very well with traditional slim tube measurements. And the beauty is we were able to do it we were actually able to make our measurements faster than the slim tube folks were able to make their measurements. So that was a bit of a pride thing that we were excited about. We're able to design, develop, and prove this out faster than some folks could make the slim tube measurement.
Perfect. I got one last question here, unless more questions come in. But what is the commercial pricing for MMP currently?
Yeah, so this is a brand new offering. So our pricing right now is sort of preliminary and trial pricing with everybody that we're working with. Our goal is to be 50% cheaper than any slim tube that's out there. And that's going to be consistent across our entire PVT line. Is we want to be by far the cheapest option that's on the market, which is, to me, I think we want this to be so cost effective that it's a total no-brainer to switch.
Right on. A couple more questions just came in. So question, how long is the channel in your microchip?
So I wouldn't be able to disclose the specifics of that at this time. But what I can talk about is the development process behind getting to the length that we have in our current chip design. And the current length of the design was arrived at by looking at a very large array of lengths, because the consideration here is, are we giving the gas and the oil enough time to equilibrate, to have enough contacts in order to reach miscibility? And so what we were able to do through a significant amount of work and behind the scenes data collection is we've reached a point where we know that the length is sufficient in order to achieve that equilibrium context. And if you're interested to learn more, I'd be happy to have a separate conversation about that.
Perfect. Another question came in. You mentioned live viscosity/density measurements. Is this available now? And I guess I'll add to that, when do you expect it to be available?
So viscosity and density are a piece of what we can do. We can do some viscosity measurements. We're not there yet in terms of full live viscosity and density measurements. We expect that to be ready, like I said, in that sort of 9 to 18 month timeline. Hopefully sooner than that, but we don't want to rush development and end up with a half-baked product, right? So the process here, and I'll just say about that, in general, we're looking for partners on our PVT development that are interested in working with us, because our philosophy behind design and development at Interface is that as much expertise as we can possibly get is always going to benefit us. And so we want to work with the industry to make sure that the measurements we're making meet expectations.
Awesome. Another question came in. What is the smallest pore size that you have been able to create in the cells?
So the smallest pore throat sizes that we use for our miscibility measurements, this is a standardized system that was designed to replicate slim tube systems. And so the pore throat sizes on these are approximately 5 microns. They can be expanded and contracted based on if there are specific needs of the customer. In our shale unconventional offerings, where pore throat size becomes the determining factor in performance, we are able to go down to 40 to 50 nanometers in pore throat sizes. which is significantly below the threshold where we start to see the thermodynamic properties of the oil actually physically changing due to the confinement. So we're able to determine those, to measure those nano confinement effects.
Great, thanks, Stuart. One more here, actually. Can you differentiate 3 hydrocarbon phases in tube? Example, CO2-rich liquid phase in low temperature, CO2 injection.
So I would say that that's not a measurement we've attempted to make yet. Our primary goal with this was to differentiate the specific, be able to bring something to market that can take on the traditional slim tube stuff. This is something we'd be really interested in investigating further. So I'd encourage you to send me an email, give me a phone call, send an email, or submit an intro on our website to chat further. I wouldn't say yes or no right now. I'd want to learn more about that question. Awesome.
And just a general comment. So Jan from Petrolab says, very exciting. So thanks for your comment.
I'm glad it's exciting. Just as we wrap up here, I think it's not very often that we come across technologies that are able to fundamentally transform how people think about an industry. And I think this technology opens up a new way of thinking about it opens up a new way of thinking about the way we work. And so it's I would challenge those that are listening now, what would you do if PVT was more accessible in general?
Mm-hmm. Actually, one last question is, how does this method compare to RBA or VIFT?
So in general, I believe that this is a more accurate measurement than rising bubble or VIFT. Specifically, the rising bubble is very good at measuring a first contact miscibility, which is good if we're looking at specific mechanisms for miscibility pressures. But in our case, we're able to measure both the first contact and multi-contact miscibility pressures. So I think this is a more dynamic and more effective measurement, where the rising bubble is effective but limited. And I would say the same thing about any visual IFT measurements. They're good measurements for what they are. We've designed a system that I believe is more robust and overall.
Awesome. I think that wraps up the questions we have. If anyone missed a question or felt like they had more things to talk about or more inquiries, feel free to reach out to Stuart himself. His email address is right on the screen there, stuart.k@interfacefluidics.com. We have a general email address as well, or reach out to anyone that you know, and generally reach out to me or anyone else. So this webinar will be available on our website and YouTube. We do have a channel that you can subscribe to, and then you'll get all of our upcoming content. This is, like I mentioned, this is the first webinar that we've done, and there's going to be many more to come. We're hoping to have a schedule put up on our website soon, so stay tuned for that. And I just hope that everyone enjoyed everything that Stuart had to say today. Just thank you for joining, and enjoy the rest of your guys' day.
Thank you. Have a great day.